Well, hello friends. Welcome back to emulator hacking. Today we're going to continue on the user space emulator, and we are going to set our sights on a program that we want to try to get running. And we're just going to go like instruction by instruction essentially, and implementing things as we go. So the program that I would like to get running is the true program, right? So it's, if you're not familiar, is this very important part of Unix. It's a program that just returns success, right? And but we don't want to jump directly to main. We want to jump into the _start function, which is where the kernel actually transfers control after loading the binary. So as we can see here, the very first thing it's going to try to do is push the base pointer onto the stack. So we're going to have to learn how to do these things. But first thing we'll do is we'll just set up the emulator to not load the main symbol, but rather load the start symbol. And then we'll just start there. Oops. Just because it'll be closer to the real thing. And later on, obviously, we want to load in like the whole elf into our fake memory and things like that. But right now, we'll just do this. And then let's try running the thing. So the UE bin true. And we immediately fail on push EBP because we haven't implemented that instruction. So let's go and do that on line 367. Right here, push a 32-bit register. So what we want to do then, or what I should say about this instruction, is that the register that you want to push, it's encoded in the instruction itself. So we can fetch that from the instruction object. So what we do is we just say, maybe we should have some kind of helper for this, but like push 32, and we have a register index, so we can just fetch it, the register from the table that we made last time. So here we go. And then all we need to do is invent this push 32 thing, but let's see how that would work. So it would be value, I guess. And maybe these should be private, by the way. So we'll add an API here, so you can push a 32-bit value if you want to. So on x86, what happens when you push a value is that first you decrement the stack pointer by the size of the value that you're pushing. So in our case, that means that we move the stack pointer size of value, essentially. And oh, we don't have get ESP. What did I call that? I thought we had these things. Oh, I didn't add either of these. Okay, well, we can just do this. There we go. And then after you've decremented, you have to write the 32-bit value to this location on the stack. So now comes the interesting part, right? Like now we have to write to memory. And we don't really have memory. We've only been dealing with registers so far. So what we'll do is we will tell the emulator, or no, let's not tell the emulator. Let's make a function like write memory 32 at a specific address. So that would be at MESP, and what we'll write is value. Okay, so I'm adding helpers like this because we're going to use these building blocks in a lot more places over time, so might as well add them right away. So here we'll want an address. Maybe we should use an x86 logical address actually. So logical address is a segment plus an offset. So it's just a simple object that it says selector and offset actually, which I guess is fine too. So it's a selector and offset, 16-bit selector, 32-bit offset. And when you are pushing on the stack, then you are using the SS stack segment. So really what we should be doing is something more like this. And I should write out those helpers because we'll add these two. SS. So the stack segment is always the same in user space, in Serenity user space. So some things we don't have to implement the full x86 CPU behavior, right? Because we know that we're only targeting the behavior of user space programs in Serenity. So let me see that I'm not choosing the wrong thing. It's data 3. Okay, yeah, I messed it up. So this is the data segment. Oh, yeah, this is data if you're in kernel space. I was thinking kernel space. So it's hex 20. And that will also be the, there will always be the data segment and the extra segment. At least I would assume. I think we don't have to deal with these changing, at least not anytime soon. Although you could potentially override them, but we'll deal with that later. For now, we'll just hardcode them. So the stack is at, these are 16-bit by the way, the stack is at selector 20 and the ESP. So here we add our memory write function, so that would be write memory 32, logical address, and a U32 value. Then it seems like we need instruction.h. Yes, okay. So I think when it comes to the selector part of the address, we'll just assert for now that the selector is 20 because I don't want to deal with other situations right now. The main other situation where in our case is going to be the thread local storage, which is not in the sort of linear address space, but it's at its own segment. That's everything else is in flat memory except TLS. So we're gonna have to deal with that when we get there, but we're pretty far away from TLS. So anyway, this is basically the logic of push. And then to write memory, we will tell the emulator to talk to his memory management unit, and we will write 32 at address value. Yeah, so this thing, we'll just delegate the responsibility to something else, and let's invent soft MMU. Okay. So user space emulator. Should maximize this for maximum fun. So this will be the memory management unit that we install in our emulator, which will help us keep track of what memory we have. Because we're going to have a few different types of memory, like we're going to have for instance, like the kernel, or the program stack, which will be provided by the fake kernel at startup and things like that. But then you could also, the program that we run, it might run an mmap syscall, and then we have to allocate some memory for that, and we want to keep track of all these different allocations. So here we will, maybe this will have like a vector of region object, let's say it's a non-null putter vector. And what is a region? It is a let's see what we can do with this actually. I guess it could have an API like this. Write 32 at an offset. And the value, right? Yeah. So let's see what we can do here. Non-null putter vector. I guess today's video is probably going to be mostly about setting up this so that we can like do that push instruction, because it will take a while to get all of the MMU bits into place. So we'll have a write 32 and then also a read 32. Something like that. And then every region should know its base address and its size. So let's just make that store that on the region itself here. So base address, size, something like that. Oopsie doopsie. We can add some getters. How about we just call it base? Actually, turn size, yes, and then maybe a helper for like finding the end of it. That'll probably be useful. Okay, so the soft MMU will have a bunch of these regions, and then it will have an API that we already tried to use, which was write 32 at address value, right? That's how we used it. Right. So we need to expose the MMU on the emulator. So let's see about that. So we'll put that here. Maybe we instantiate that before the CPU even. Okay. And now we will just only pass the offset. There we go. All right. And then what do we want to do in this API? So I guess we need to find the relevant region for the address that you're giving us. So we'll do something like this, find region for address. This is not going to be particularly efficient, but that's not our main concern. We just want to build something that works, and then we'll think about performance later. Because the important thing with stuff like this is to get sort of the right abstractions into place, and then you can always optimize the details later. As long as you have good abstractions, it doesn't really matter how it works internally, which is really nice. So let's see, if we don't have a region, I guess, so this would be like an out of bounds write, essentially. So for now, let's just assert not reached, because we don't really have a way to, we don't really have something that we want to do in that situation right now. But later on, obviously, this is going to become sort of the bread and butter of this application, is like detecting situations like this. But right now, we'll just skip over it. So actually, let's put it to do here. Okay, so now we've found a region. So then we just want to call, oh, actually, we don't know what find region is yet. It will be region, find region address. There we go, and then we can just say region right 32, address minus region base, because that's the offset into the region, and we write the value there. Okay, so that's really nice. Let's do the same for read 32 actually, because it's easy to duplicate. So same basic concept, find the region, and then return a read 32 from the region at the correct offset. Great. And then what does find region actually do? So it will be something like, I guess we can just do this. For every region that we have, we'll just say if region contains address, return region, otherwise return null footer. And then we need a contains here, which will just be like address is here and address is less than end, right? There we go. See, we found a use for end immediately. And yeah, that's pretty good. So okay, so these are pure virtual, right? So we need to actually subclass region now and give ourselves a stack. So let's see. I guess we can commit that little change we did in main first of all. So here we'll just say like user space emulator. This name is a bit of a mouthful, by the way, but maybe we'll get used to it. Otherwise we'll look for a new name. But right now we'll just say start executing in start instead. Name. This is closer to the real thing. One step closer to the real thing, yeah. All right, and then, so what would it look like when we set up a stack in the CPU? So let's do that in the emulator class, actually. So here, after we've set that up, we'll do like MMU, we'll do like add region, and we move some region that we've instantiated. Okay, so stack region. Actually, let's put this in a helper function just to keep things a little bit separated. Okay, so this will be a I guess for now we can make our own class for this. So like, or simple region. Let's just invent a simple region, and we give it a size. So the size is going to be, say, 1 megabyte of stack, or maybe we do something much smaller. Stack size. Something like that. And we'll put the stack at this address maybe. Here, it's kind of a, I don't know, we just need to put it somewhere, so let's put it there. And then we have to invent this simple region class. I think we can, maybe we can just declare it here for now. So class simple region final is a public soft MMU region. And it has a base and size parameters. Sure. So I guess we call the base class. Forgot to add a base class constructor, I think, yeah. So we'll just make a protected one here. Okay, something like that. And then the interesting part here, of course, is going to be that we allocate something. So we will malloc size bytes and put that into our little data here. Something like this. Then we have to cast a mundo. Okay. And now for the interesting part. How do we actually read here when we get told to read? And how do we write? So we should probably keep track. Oh, we know our size actually. It's in the base class. So here, all we need to do is just say, let's assert actually. Assert contains offset, and we'll also assert that it contains the entirety of a 32-bit quantity here. Otherwise, we'll have to deal with situations where you have like a memory access that spans across two regions, because that could happen, right? Because you could have like you could mmap in such a way that you have like two separate regions next to each other in memory, and then if you do a read that crosses the region boundary, then we need to handle that. But right now we'll just assert that that's not happening, because it'll be a rare situation, but it's something we do have to deal with eventually. Anyway, so then we can just do return mdata. We cast plus offset, something like that. And likewise here, we just write to it. So one thing that's really comfortable here is that we are emulating x86 on x86, so we know that it's little endian, so we don't have to think about byte order. It's like one less thing to care about. We don't care about emulating. We're not going to run this emulator on a big endian system. At least I'm not. So that simplifies stuff like this. Otherwise, you would have to think about the byte order. Okay, so I guess there we have it. Let's see if all of this compiles. No, we forgot to implement add region. Right, soft MMU. That's the region API, and then add region is gonna just be like, you just give him a non-null inputter to region. And you know what, let's do that out of line, because we probably want to do some like sanity checks and stuff in there. Soft MMU, add region. Okay, and then we can do something like assert that we don't find a region for the base of this region. and that we also don't find one. Let's just start with that. That's fine. Fix me more sanity checks, please. So there we go. Right, the CMake lists. Where is it? Here. Okay. Okay. And now we're starting on 61 in soft MMU, okay? That we are, where are we? Here, so we didn't find a region for this, right? Oh, yeah, of course, because what are we trying to write to? We're trying to write to the stack pointer, and where's the stack pointer pointing to? To 0, probably, so we didn't set that up correctly. So here, let's see, stack location. I don't know, we're just saving the constant somehow, and then what we'll do is we'll just set the stack to point to the stack location, and now we need that setter. Wait. I'm not braining correctly. So the on x86 the stack grows downwards. So if we have a 64 kilobyte stack starting at this address, I can't set this to be the stack pointer. The stack pointer has to be at the very end of the stack. So actually past the end of the stack. So what we'll do is we'll just say stack location plus stack size. Because if you recall how we implemented the push operation, what happens is that first we decrement by 4 bytes, and then we write to that location. So we want to be just past the end of the stack initially, and then the very first push will decrement it by 4, and put us inside of the stack region, and then this should work. Okay, dang it. I guess we're gonna need to have some help here. So 61, this thing is failing. Oh yeah, right, because the offset is, we've already subtracted the way we were calling these. We had the MMU subtract here. Maybe I'm thinking maybe we should let the memory implementation deal with that. Or I'm not exactly sure. Maybe it's better that the MMU subtracts it for you, and then when you end up in your region subclass, then you just get an internal offset. But then we can't do contains, because contains operates on the global base address, not the local base address, which is always 0, right? So I guess this is just a matter of doing this. So essentially that's what we want to check. All right, finally, running some code. So look at this. We're getting through suddenly quite a few instructions. So we're pushing EBP on the stack. And then we're doing some mov, and then we're pushing more registers on the stack. Of course, all of these things are like kind of uninteresting values at first, but you can see here, we push EBP, so this goes on the stack, and the stack pointer is decremented by 4, as you can see here. And then we mov stack pointer into EBP, so EBP takes the stack pointer here, and then we start pushing more stuff, and the stack pointer decrements, and we are 64 kilobytes above the hex Fagillion address that we use for the stack. So everything here is looking very good. Maybe for our own interest, we should just print out memory writes right now. Write memory 32. I think that might be just kind of interesting at this point in time. So maybe we'll do it in here. Or let's do it in the CPU. And then we will write the address here and the value that we are sending in. So address value. Oops. Should we just write them like this maybe? Offset. This will be nice so we can see what we're actually writing to memory. Maybe I should have put that in a separate color also. So yeah, we can see here, push EBP is a write memory, so it writes the value 0 to this address. It's absolutely perfect. And that's great. How about we set things up so that EBP has some other value than 0 at startup, just to test out that this thing is actually working. Let's put some color on this guy also, just for funsies. So when we set up the, I guess when we set up the CPU, we can just initialize the EBP to be cool, right? And just verify that that's what we actually push. Clickety click. Yes. Write memory 32. We are writing cool to this address. Very good. Okay. This I didn't like that color. Let's choose a different color. Okay, so that's nice. Let's implement read as well. So, because it will be very similar anyway. Read, return, and I guess we can do this, and then we can print out what we actually read. There we go. Return value. Okay. We'll use a different, yet another different color here. All right, and so this would be useful for implementing like the popped instruction, right? For popping something off the stack. So it would look something like, it would look like this. And you would read memory 32 at the current stack location. Oops, auto value, and then you would increment after that, and then return value. That's basically it. So So if we had like pop reg 32, the way we would implement that now is we would just do exactly the same thing that push does, except pop instead. So pop 32. Boom. So yeah, that's essentially it. Like, we didn't have any pops in our instruction stream yet, right? So we stalled on something else. But I think I'm probably going to be done here for today, because I just wanted to get like some basic memory management up and running, and just sketch out the general shape of things. So what are we dying on? We're dying on a subtract instruction. Okay, so subtract this constant from the EBX register. That'll be something to implement later, but now we have the beginnings of memory, and that's great. So one thing is, obviously, I should note that I understand that this is not a very optimal way of laying out memory, because we're gonna hit this thing very often, and like having to scan through this list of regions every time is not going to be very performant. But this is something that can be replaced later, like with a different data structure, without changing the sort of the higher level abstraction, which is what I was saying earlier. So we'll build it in this simple way for now, and then later we can come here and put in caches. We can put in like a tree instead, so that you can do, you know, log n lookups of regions and things like that. But for now, this is good enough. So let's commit our stuff. Do the MMU first. So you, yes, you, no stack for you. Actually, yeah, let's stage that, but not these guys. Yes. No. Okay. Space emulator. Add a simple soft emu class. Start sketching out a soft emu class. This emulator sub-object will keep track of all active memory regions and handle memory read-write operations from the CPU. A memory region is currently represented by a virtual region object that can implement arbitrary behavior by overriding read-write ops. Yeah. Okay. And then this is about adding a stack. So yeah, let's just do this in one big go. Add a stack at an initial stack region, initial stack, and implement push reg 32. Yes. Programs now start out with a 64 kilobyte stack at yeah, that's pretty cool. So actually, let me remove that cool. Oh, I already did. Okay. So yeah, I think this is going to be it for today's video. So just got the basic memory read and write up and running. Obviously, we can only do 32-bit read and write right now. We're going to need 8-bit variants, 16-bit variants, and so on, but one thing at a time. So this is cool. Can make a little progress here. And then that will be our next thing. I don't know if I would implement that in a video, or maybe I would do it offline, because this kind of things are just implementing like arithmetic is not super complicated, but we'll see. Anyways, if you made it this far, then thank you for watching the video and for hanging out. I hope that you saw something interesting here, and I think this is going to be a very fun project to work on. So thanks for checking it out, and I'll see you next time. Bye.